In this session, we are going to study cantilever beam with uniformly distributed load. So suppose we have cantilever beam like this, and there is UDL like this, right? We have shown that UDL can be shown by this symbols, right? And this is, suppose the load is W kilonewton per meter. This is our fixed end and this is free end. And when we want to draw the shear force and bending moment diagram for this cantilever beam, right? So as usual, we will take a cross section at any point. Suppose we are taking from free end. For cantilever, it is always better to take the cross section from the free end, right? Otherwise, here moments are unknown, so it will be difficult to find out the value here. So you will take from left, it will be difficult. For free end, it will be good to take although you can take from any side, but it will be better to take the cross section from the free end. So suppose the length of the section is L, length of the beam is L, and we are taking any cross section, say like this. At any point you can take. So suppose this is a cross section here, and this is X cross section at a distance X from the free end. At a distance X from the free end, we have taken this cross section, capital X, right? So at this cross section area, we want to find out what will be the value of shear force and bending moment, and that value we will utilize to find out throughout the shear force and bending moment diagram, right? So first of all, let us find out shear force. Shear force at X, Fx. Now, you know that we have already told you that the shear force for UDL is like this, that there is a brick, of rectangular cross section placed at some place, and it is uniformly distributed like this, and its load will be acting at the center, right? And total load will be, if it is W kilonewton per meter and this length is X, suppose this length is X, then the load will be W multiplied by X, W into X, because the area of the rectangle is this multiplied with this side, multiplication of two sides. So this will be Wx, right? And this will be at the center, means these distances will be x by 2 and x by 2. X by 2 and x by 2, right? And Wx will be at center, right? So similarly, same thing we are making here, that this load is acting at the center here, and this much is W multiplied by the X. So Wx at the center, right? So this distance we have taken X from the free end, and this will be the X by 2. This distance will be X by 2. Is it okay? Now, so, and there is no other force, only UDL is there. There is no any other point load or any other load. So it is very simple case. So what will be the shear force at X? So it will be the algebraic sum of all the forces to the right or left of the section. So all the forces, what is the force to the right of this section? There is only Wx, and it is downward. And to the right of the section, if something is downward, it is taken as positive. So Wx is the load, Ws is the shear force at a cross section X, Wx, and there is only one force at to the right of the section, right? Although it is a UDL, but it is having a concentrated load at its center of gravity, and this is Wx. So this is the only load. This is at the right of the section X. Now it is varying. It is varying because it is variable. X is there, right? Linearly varying, right? So what we can do, if we want to find at B and A, we can put the value of X as 0 and L, right? For finding the shear force at B, X will be 0, so this will be 0 because X is 0 at B, and at A that will be WL because X is L at A, right? So 0 to WL it is varying and variation is linear. Now it can be drawn very easily. So you can draw like this. It is 0 at this end, B end it is 0, at A end it is WL, this is WL, right? And it is varying linearly from A to B. This is our A point. It is varying linearly, so draw a linear line, straight line matching with B point, and you will get your shear force diagram, right? So this is a straight line, straight linear line, right? Straight line, and it is positive, and it is positive. So this is our shear force diagram for cantilever beam with UDL. Shear force diagram. It's so easy to draw. Now we want to draw bending moment diagram. This was shear force diagram. Now we want to draw bending moment diagram. We will find out the bending moment at X. What will be the bending moment at X? And what is bending moment? It is the algebraic sum of all the forces, a moment of all the forces. So take the moment of this Wx with respect to X. This will be Wx multiplied by X by 2. So moment of X, moment of Wx with respect to X will be, the distance is X by 2. So this is X by 2 because it is acting at center at a distance X by 2 from the X, right? So Wx multiplied by X by 2. And what type of movement is this? This is clockwise at right. Clockwise at right it is negative. Clockwise at right it is negative because it is a hogging bending moment, right? So this is negative. Is it okay? So you will get, this will be minus Wx square by 2. Wx square by 2. And it means it is parabolic. It is parabolic, right? So if we want to find out at endpoints at A and B, so what will be the moment? And there is no other force, so it will be valid for all the cross section. So M will be equal to 0 when X is 0 and X is 0 at point B because we are taking from B, right? And M will be at A where X is L. Put the value of X as L minus WL square by 2, minus WL square by 2, right? Minus WL square by 2. So draw the diagram now. This is our base. This is 0 at point B. This is WL square by 2 in negative direction, and the curve is parabolic with convex inside, right? So this type of curve is there, right? Negative because it is negative, right? And what is magnitude at A? That is WL square by 2. This is A point, this is B point. So this is our bending moment diagram. Bending moment diagram for cantilever beam with UDL.